Okay, yeah, so I will be talking a little bit about this subject area of normalizing flows for lattice field theories in general, but I guess also hopefully by the end of lecture 3, a little bit about how one can specialize to the gauge theory case and what's interesting or challenging there. Let's see, is there anything I want to summarize? So yeah, I think this might be a bit of an experimental approach to giving these summer school lectures. So I've got some small amount of framing material, motivation and such in slides, but then I'd hoped to do an interactive bit of coding, which could be a disaster, it could be all right, but we're just going to try it today and see how it goes, and if it's terrible, I'll readjust for the remaining lectures. Okay, so let me get started. I guess normalizing flows are a pretty opaque name. I know not everybody really knows what they're about. So let me zoom out and go to a bit of motivation first. So who is familiar at all with Markov chain Monte Carlo? Is this familiar to most people? Okay, great. This is kind of the engine of our field, so that's not too surprising. But as a very, very brief reminder, the idea of what we like to do in lattice field theory in general is to estimate observables, as written here in the top right, which one can think of as some thermal expectation value in a quantum field theory, with some kind of discretized path integral, where I'm talking here about an integral over degrees of freedom that correspond to some field, so degrees of freedom that are associated to either sites or links of some lattice, and they're distributed according to, in the Euclidean signature, e to the minus s. But as Gert also mentioned, this could be a statistical model as well, where we think of S as an energy instead, and exactly the same principles apply. And so, of course, this is a very high-dimensional integral, so the traditional way that we approach this is with Monte Carlo sampling. So we say, I'm going to draw some configurations. Maybe I can actually use this. I'm going to draw some configurations from this distribution that's defined by this probability measure. And as long as S is real, that's all OK. And for the purpose of this talk, we'll just stick to real actions. And then we can approximate this thermal expectation value by the sample mean of measurements over those samples. And the nice thing about this is it's systematically improvable. I draw more samples, and my uncertainty on this estimate goes down in principle. Now, of course, drawing these samples, that's potentially a challenging problem. That's kind of at the heart of the motivation for this area. And the traditional approach to this is to use Markov chains. So the idea there being we start from some arbitrary field configuration. Maybe this is some gauge field. This is a visualization of the topological charge density in this case. And I apply a series of stochastic transformations to that field that are designed to equilibrate to a distribution that is exactly as such, e to the minus action. And I think probably Jakob will say a lot more about how we actually design these Markov chain simulations, which is the traditional approach. But just to highlight kind of the difficulties here, when we're talking about lattice gauge theories at the frontier, the state of the art, we're talking about four-dimensional grids, of course, because this is space-time. And if this is SU3 gauge theory for QCD, then these are 3x3 matrices associated with links of the lattice. And if I make a crude estimate of what we do in the state of the art, we might have up to this number, what is this, 10 billion components per a single gauge field sample, which is, of course, a very high-dimensional data space. Now, the main problem, so that's kind of the fundamental scale of the problem. And the main problem is that not only do we have this large computational cost to manipulating these gauge field configurations, but the Markov chains themselves become inefficient as I go to the continuum limits, as I take the lattice spacing smaller and smaller. And this issue goes by the name critical slowing down, which can be sort of qualitatively summarized as this problem in Markov chains of traditional Markov chains involving some kind of local updating to the field. So there's some correlation between the previous sample and the next sample after a given Markov chain step, meaning I need to take many steps to decorrelate sufficiently. And the smaller the lattice spacing, the more steps I need to take to sufficiently decorrelate my samples. There's also this related notion of topological freezing when you have, say, different topological sectors or vacua of a broken symmetry, wherein this Markov chain, because it is locally updating the field, tends to get stuck near specific minima and takes a long time to tunnel. And this is a related but distinct notion. And in fact, you can go and measure this. And here's an example of, on one particular, I believe this was a pure gauge theory, as you take the lattice spacing smaller and smaller, the simulation cost in this case was diverging consistent with exponentially with respect to the lattice spacing. But in general, it's just diverging as a goes to 0, which is a big problem for the types of physics that one can access at the end of the day, because of course we need to take that continuum limit, as Alberto also mentioned as motivation in his talk earlier. Okay, so this is kind of the foundation. We have this issue, and Markov chain Monte Carlo is a very successful approach to solving our lattice calculations to date, but maybe we'd like to find a way around this. We'd like to look for new methods that can circumvent this problem of critical slowing down. And what I'd like to start with as kind of motivation for moving in the direction of normalizing flows is relating this Monte Carlo problem on the lattice to image generation. I'm missing the obligatory dogs and cats, apologies, but I've got at least some fictitious faces that were generated from generative AI, so hopefully that's close enough. And so one could compare these two types of problems. Let's say I'm tasking a generative AI model to generate images that look like real human faces. These are not real people, of course. These are the generated images. And when I think about that sort of problem, it has this, this manifold hypothesis that I think Hert also mentioned earlier, that the typical samples form a very small corner of the total phase space, if you like, of the images that I could write down. And if I just randomly sample an image with no kind of concentration or probability distribution over it, a typical image will just look like white noise. Whereas, what I mean by that is a random image will just look like white noise, whereas a typical image from the set of the support of the data that I'm interested in is a much narrower subspace of that total space that I'm working in. And I would argue that the same thing holds for the lattice sampling problem, in the sense that when I'm talking about a particular action, so that's some bare couplings that corresponds to some lattice spacing, I observe that my fields that I sample tend to have fluctuations on a particular length scale, and they have a particular power spectrum, if you like, of fluctuations at varying length scales that is very well represented across the lattice in typical samples. And in contrast to the total space of field configurations I could be sampling in, this set of configurations is, if you like, a very small or low-dimensional subset. So in that sense, maybe we could imagine that these models that work well for capturing such subspaces of image distributions could do the same for the lattice sampling problem. Okay, so this intuition is the same as the talk earlier this morning. One thing I will highlight, though, is what I find compelling is that when we proceed, and when I talk about normalizing flows, we will be able to demand that the models that we construct produce unbiased results. And I think that's an important feature of the kind of sampling approaches that we're looking into. Another kind of challenging feature, perhaps, of trying to apply generative AI to this problem is that whereas for images you have lots and lots of images on the internet, we don't have lots and lots of gauge fields on the internet, or maybe we have some, but we don't have as many as we'd like. There's this inverted data hierarchy, is perhaps the best way to say it, that the number of samples that you have at the resolutions or at the lattice spacings that you're interested in is far smaller than the number of degrees of freedom per sample. So if you imagine something about trying to estimate the structure of your samples, you have not that many data points to estimate a structure in a very high dimensional space. But we also have some advantages compared to the image generation problem. In particular, I can write down the action for you after discretization analytically. If you hand me a gauge field configuration, I can just plug it into my computer and I get a number back. And that's not something you can do for the likelihood of images. I can't tell you exactly how likely an image should be. There's no analytic distribution there for faces, for example. And maybe also importantly, we know physical symmetries of our field theory, which is, of course, encoded in the action, but we can isolate these. And hopefully in the third lecture, there'll be enough time to talk about how these symmetries can be made manifest also in the models, which makes it a bit easier to train the models and to capture the right distributions. OK, I should also say, please feel free to interrupt me if I'm going too fast or if you have questions. I'm happy to take questions at any point. OK, so with that motivation aside, the big question is, can we use generative AI writ large? But maybe more specifically in this set of lectures, can we use normalizing flow models, which I'll get to in a moment, to solve this critical slowing down problem for lattice field theory and lattice gauge theory in particular? With the general picture that I would like you to take away from this, if nothing else, is that this Markov chain Monte Carlo, where I'm doing an iterative update to my field configuration, which is causing the critical slowing down, maybe I can break that chain and replace it with this approach of generative AI models, which, though I haven't mentioned it yet, the structure of these models typically involves starting from some independently drawn random noise, passing it through a deterministic transformation, or possibly a non-deterministic random transformation, and outputting what should hopefully be a sample distributed according to this e to the minus action distribution. And because this is a totally independent sampling procedure, there's no correlations built into the samples drawn from this approach. So that's the idea of why it could conceivably solve this critical slowing down problem that has to do with Markov chains. So to give a bit of a bird's eye view, then suppose we had such a model that I could feed random noise into, and it does some transformation. Maybe there's some details in here that we could get to later. And it outputs a field configuration that's typical in some sense, or in a more precise sense is distributed when I pass this distribution through, is distributed according exactly to e to the minus action. Well, sorry, let me say that differently. This is a parameterized transformation, and I get out some sort of samples from this if I feed in random noise. And what I'd like to do is iterate on the parameters here so that after I've done this so-called training process, which you can also think of as just a variational optimization of the parameters inside this transformation, I'd like it to be the case that at the end of that process, I have that feeding in this particular distribution of random noise through the transformation will output the right distribution of lattice field configurations. And so, of course, the devil is in the details. What does that training procedure actually look like? That's at the heart of this normalizing flows approach. But the idea is that, OK, so if we do this parameterization using, for example, machine learning tools like neural networks, there's a very nice way to do this training step involving backpropagation of gradients, which allows me to, for example, write down a loss function that tells me, is my model quality good in terms of reproducing this distribution accurately or bad? And then I can take the gradient of that function and iteratively improve my parameters, basically by gradient descent. And finally, if I do this enough and I get to a good quality model, I can just save it. And the idea at the end of the day is that because these samples that go through the model are totally independent, I can draw these samples in a very parallel way, which is a nice feature. There's no Markov chain involved in this, so there's no critical slowing down in that sense. And in particular, in a way that I'll talk about in a moment, we can also apply bias correction if we use certain types of generative models, so that the end distribution is a perfectly unbiased sampling. OK, so let me now start scoping in towards what this generative model could look like to satisfy all these properties that we wanted, to be able to train it this way, to be able to do the bias correction. This is a particular survey of image models. It's of course not complete, but it actually captures many of the big classes of models that have been looked at over the past decade or two. Maybe you've heard of these generative adversarial networks, these GANs. They were popular in the ancient history of machine learning, by which I mean probably the early 2010s. And they're now a little bit out of vogue for whatever reason. They involve some kind of transformation process, if you like, that takes some random noise. This Z will always be the random noise in this case. And it passes it through a transformation that outputs, hopefully, an appropriately distributed sample. And the way the training works in this case is to trade off against a discriminator that compares that sample versus data. We're going to set that aside because it, as well as the second class, which is quite similar, this variational autoencoder, does not have an ability to apply bias correction. What I will be talking about is this flow-based model. I'll get back to that in a sec. But let me just say also, diffusion models you've heard about this morning. And I'm going to basically leave it to Gert to go into detail on that, or I guess has already gone into detail on that. But in many ways, I think there's connections between these diffusion models and flow-based models that I will talk about in just a moment. And the idea in both cases is that one applies some kind of transformation, much like these other models, between the data that you're trying to represent and random noise. So either you go from random noise to data. In this case, it's written as the inverse. Or you go from data to random noise. And same thing here with diffusion models. You go from either data to random noise or from random noise to data with two different kinds of processes. In the flow-based case, we're working with a deterministic invertible transformation. With the diffusion models case, we're working with a stochastic differential equation, as Gert wrote down earlier, but with similar objectives. OK, so let me zoom in a little bit on these flow-based models then. And I'd like to motivate this all by talking about a concrete flow-based sampler, which is a very actually ubiquitous tool. It's this Box-Muller transformation that's used to sample normally distributed, so Gaussian distributed random variables on computers in a way that's tractable to handle and efficient. And so the idea of this approach, this transformation, is if I start from the uniform distribution on the circle, which this is something that's easy to produce on a computer because I can get a uniform distribution, let's say on the square, and I can just discard points that live outside of this unit circle. That's one example of a way that you could do it. So as long as I have some random number generator, I should be able to get this uniform distribution. Then I apply this particular transformation to the points x and y that I've just sampled in this uniform circle. And the transformation amounts to just rescaling the radius. So it's this particular funny function of the radius, this root minus 2 log r squared over r. Whatever it happens to be, it squishes and stretches the points so that the points at the very edge of this unit circle end up being mapped all the way off to infinity. The points near the center stay pretty close to the center. And the way the distribution is designed is such that we concentrate the points sort of near the peak, but with this Gaussian fall off towards infinity. And in fact, you can go and compute the transformation that's being done here, the Jacobian of the transformation. And the important point here is that the picture is that I started with a simple, what I'll call a prior probability density. Sorry, it's a little bit low on the slides. The notation I'll use for this is typically R for the prior probability density. And this transformation is the flow. So it is a transformation that's invertible and differentiable. And the result of that is an output density which is calculable by this change of measure formula. So I'll have some output density from this transformation, which I'll continue to use the notation Q for these sorts of output densities from flows. That's equal to the prior density of the point that I sampled, which in this case is just uniform, so it drops out, times the inverse of the determinant of the Jacobian of this transformation. And that simply comes from literally the squishing and stretching factor of how much did the points in some small patch around where I started get squished or stretched by this transformation of the radius. So of course, this is kind of a magic transformation. It happens to satisfy, if you work through the math, this property that the output distribution is a Gaussian distribution. Oh, by the way, this is actually how the C++ standard library draws random variables from the Gaussian distribution. So if you're using that, you're using normalizing flows. Maybe you don't know it. But OK, so I think the general point here is that we wrote down this magical transformation that took us from an easy prior density, and it outputted the right distribution. But that's typically not what's going to be the case. We won't know the right transformation that we're after. And so the more general picture here is to say, let me fix maybe some easy prior density, anything that I can sample from, and I can compute this probability density function R. And let me, instead of applying some fixed transformation that's differentiable and invertible, let me apply a parametrized transformation that's a diffeomorphism, so differentiable and invertible. And whatever that output distribution is, it's computable. I can write down this change of measure formula, so the prior density times this Jacobian factor. And I can hope to optimize the parameters of this transformation such that at the end of the day, this distribution is close to the one that I'm after. So this is the big picture. So moving from flows that have no parameterization, no optimization, to this more general picture just involves making this transformation function that you're after something that's parameterized and, in principle, something that you can optimize to achieve the target that you're after. And so, for example, OK, this cartoon on the right is showing you how you transform by some sequence of squishing and stretching motions, or in other words, this flow, this diffeomorphism, from a simple Gaussian distribution to this complex target. It's a double crescent moon, which is often used in the machine learning literature. And so the transformation parameters here were optimized exactly to reproduce that target that one was after.
Since you compare the real distributions, does it include the normalization? So in other words, is the normalization preserved?
Yeah, so this flow, this calculation preserves normalization, which also means, for example, that one can compute partition functions by the by. So if you use this to sample your field theory, you actually get access to the probability density, including the log z factor. But yeah, that's exactly right. So the output of this is normalized as well. Yeah.
seem to make the most efficient path to the endpoint?
Yeah, that's a great question. So one can notice that what you're doing here is kind of very artificial, right? And the reason for that, the way that these transformations were designed, and you can kind of see it visually, is it updates one of the two coordinates at a time, condition on the other coordinate, and then composes a sequence of these transformations. And I'll actually get back to that in a moment. That's one of the strategies to design these flows in a way that manifestly preserves invertibility. But what you're talking about, there would be some like most efficient path, if you like, that just by the minimal motion moves the points to the closest point on the distribution. This is the problem of optimal transport. And people are interested in this. It's a whole field independently of machine learning, but also tied into many machine learning problems. And if you restrict yourself to that, of course, you have a very particular kind of transport problem that you're trying to solve. So maybe you can write down some approach to trying to solve it. But the nice thing about this approach of saying I'm not going to prescribe the path is that any path that gets you to the target will do. And so it gives you a larger search space in some sense. That's essentially the idea. So why we take an inefficient path. Very good. OK, so I alluded to this in the previous slide, but the idea being that if we are after a more complicated distribution where I don't have this magic transformation, maybe we can instead approximate that target distribution by parameterizing some sort of ansatz for this flow f. And I call it a flexible ansatz, but what I mean by that is potentially using machine learning tools like neural networks and so on, which for the most part, although maybe we'll dig into it a bit later, for now one can just think of this as a black box function approximator where I can increase the parameterization complexity to increase the quality of my approximation. So how do we actually potentially construct these learnable transformations? And the main challenge, OK, so maybe I should say this first. The main challenge of constructing these is that they have to be invertible and differentiable in order for me to be able to extract that change of measure formula. Otherwise, I wouldn't be able to compute what is the output probability density. And as a result, I wouldn't be able to, well, many of the methods I would use to optimize these flow-based samplers wouldn't work. But also, computing this output density, as I'll get back to in a moment, is necessary to do a bias correction. Because I want to know what is the density sampled by the model so I can compare it against what was my target e to the minus action and perform a correction, or apply a correction factor. So assuming that this is necessary, which it is for normalizing flows, how do we ensure this invertibility with a very flexible parameterization? And I would say there's roughly two strategies that have been pursued. One is we compose a discrete sequence of transformations. So we're kind of tossing out the notion of a continuous flow in this case, and we're just saying it is just some diffeomorphism that's constructed by composing individual transformations G1 through Gn, which are potentially much simpler, but can therefore be constructed to manifestly guarantee invertibility and can be constructed so that their Jacobian determinants are efficiently computable. And then the total flow by composition might be a much more complicated beast that is hopefully more flexible and can approximate what I'm after. And then the second approach, which is maybe a little bit more intuitive and fits more in this framework of flowing samples around continuously, is what I would call continuous flows. And the idea there is very similar, except instead of applying a sequence of transformations that are individually constructed to be invertible, instead I say my map from my initial random noise sample to my output is going to be the solution of some ordinary differential equation. And I'll just write that generically as saying that the time derivative in this fictitious time coordinate of u can be written as the gradient of some sort of scalar potential of that u. And here, OK, I've written this to the left of my gauge field u because I want this to live in the Lie algebra. That's just a technical detail. But it's something that in principle I can integrate in much the same way that in lattice gauge theories, when we do Markov chain sampling, which hopefully Jakob will come back to, we integrate differential equations over gauge fields. Same idea applies here, except the differential equation that I'm integrating is according to some learned scalar potential rather than some given action. And the nice thing about this is that the Jacobian factor is given also analytically in terms of that scalar potential, just in terms of the Laplacian of the potential. So in some sense, the Laplacian of the potential is describing, well, where the potential curves downwards, the samples tend to flow away from that point, and so the density goes down. and where the potential curves upwards, the samples flow towards that, and the density goes up. So that's just encoded in this equation here. So we can compute the Jacobian of the transformation. It's invertible in either case. Perhaps to give a slightly more concrete picture of what this looks like in a toy 2D example. Mostly I just threw this in here because I made this figure for a review paper and I thought it was nice, and I didn't want the work to go to waste. So if we imagine that this is some two-dimensional distribution, that we start from a normal distribution, and I'm after some kind of bimodal distribution like this, the way you might end up sampling it with a continuous flow is depicted here in this fictitious time coordinate on the vertical axis. And you can see that each point follows some particular trajectory to end up sampling around this bimodal distribution at the end. And of course, the key property of this is that I can also now go and compute what is the density Q of any given point by applying this, by calculating this Jacobian factor. OK, so I've said a little bit about some of the strategies. I'd like to just put this in the slightly broader context. So I've talked about an approach to constructing these flows using discrete transformations or using continuous transformations. And in neither of those cases did I specify what path you have to take. And this will go back to your question as well, Arthur. So I didn't specify at all how I should transport from samples from my trivial theory or my prior distribution to my output target, which, for example, this may be used in the gauge theory context to transport from, let's say, the beta equals 0 theory to the beta equals something, say 6.0 in the Wilson gauge action. These paths were not prescribed in either the yellow or the pink case, but there's more general options or alternative options that I can consider. For example, I could just try to fix a particular path that I want to take. And the advantage of this, so in some sense it goes back to, well, you have a more narrowed search space. Now I'm trying to reproduce a very particular transformation route from one distribution to the other. So you've restricted yourself severely, but the advantage is that I know potentially something analytic about this path. And in fact, Lucher's trivializing flow, which he put forward in this paper, also associated with gradient flow. So if you've worked with gradient flow, this is a related idea. Talks about how we can write down the sequence of this transformation rather that goes from gauge theory with beta equals 0, which corresponds to infinite coupling, all the way to a gauge theory with some finite coupling, finite bare coupling on the lattice. Following this annealing trajectory, if you like, where I just increase my beta incrementally according to flow, some fictitious flow time from 0 to 1. So I just designed some schedule that says my beta increases. And the nice thing about this is I can say some things analytically. In Lucher's paper, he does a perturbative calculation of to some order in this flow time t, what should exactly that potential phi look like to do this transformation. But of course, we can also approach this problem from the machine learning perspective, just keeping in mind that now we're targeting a very particular path. So that's one option that one can take. And it's also worth mentioning that instead of writing down an explicit fixed path, I can, by other means, fix a path that I'd like to take. And I would say the diffusion model approach fits into this category of there's a particular path between the distributions I'm taking that's described by the sequence of adding noise into my samples, as you saw this morning. And I couldn't tell you what these intermediate distributions are, but there is a particular sequence of distributions that I'm supposed to take that's described by this process. And that's what the learning task is to reproduce that particular trajectory. So there's various pros and cons to these approaches. I think to not overload the matter, I don't want to necessarily say like the finer points of why one or the other might be useful. I think it's more helpful to just have in mind that there is this big landscape of different approaches, and it's not entirely clear what is the best way to actually eventually find an arrow that takes us from a trivial theory to samples from the target theory that we're after in the most efficient way possible.
Sorry, when you say an explicit fixed path, is it like evolution equation or something, which is evolving with beta or something?
Yeah, so this explicit fixed path literally means I write down that I want to, maybe I can actually write this on the board. What I want is my theory or my target distribution at t equals 0 is going to be e to the minus, well, beta times, let me write it this way. I'll write the full gauge action here. So you have beta times real trace, sum over plaquettes, U plaquettes with beta equals 0. And then at all points in between, I say, let's say I'm at t equals 0.5. Then my target distribution is going to be the same thing, but with beta equals, in this case, if my target eventually is 6.0, 3.0 at this point, and then at t equals 1, I want to have finally reached a distribution described by this form, but with beta equals 6. So it just very explicitly tells me what should my distribution be everywhere in between. And so you could think of this as like I'm trying to map my samples according to the Euclidean path integral for a running value of this Baire coupling that changes as my flow time goes on. And so that's obviously going to change the structure of the distribution, and that's what should be captured by the transformation you're doing to your samples.
And for training, do you use only one beta value or something like that?
So I'll come back to training in a bit. That's kind of a complicated question, and I think I actually might not say anything about training this approach because there's many ways you could approach it. Training in the freely learnable approach, I will say something about in the next lecture. But let's go one step at a time here. Any other questions? Yeah.
In the spirit of optimal transport, do you think there's a way that you could write down some kind of cost function with respect to which any or all of these models, when trained, is optimal in some sense?
Sure. I mean, I think it's likely that one could write down some kind of loss function on top of these flows that says, even in the case where these paths are free, I now try to impose that the path that should be taken by that is close to the optimal transport path. And what you want there is that the motion of your samples is as minimal as possible to get to the target. So you could just imagine putting down some kind of cost function that penalizes the magnitude of the transformation of the samples. Very explicitly, in the continuous flows case, you would just penalize the magnitude of this vector field. So you say, I want that to be as small as possible and yet still map me between the two distributions, and then you get your optimal transport. All right, very good. OK, so I mentioned this towards the start, but I think it's very important to highlight exactly how one can impose some sort of bias correction or exactness onto these models. And so, of course, if I just write down some ansatz and I optimize it to some extent, I will get an answer that maybe is approximately correct, but is certainly not equal to the distribution that I'm after. So my samples will be slightly biased, potentially. And that may be good enough to get some qualitative information, but it's important for the sake of doing quantitative calculations that we're able to remove this factor. And in fact, because these normalizing flows give us access directly to Q, to the probability density that's being sampled by the model, and that comes from being able to compute the Jacobian factor, then exact bias correction is possible. And the simplest way to see this is by imagining just sticking in some reweighting factors. So I say I know what my probability was that I drew this sample from the model. I know what the probability should have been. So let me just reweight those samples. And this is possible, again, only because we can compute this model density that is being sampled at the present moment. So the key feature of normalizing flows is they provide you an efficient way to draw samples, and they provide you an efficient way to compute the density of those samples. So when I have both of these things, then I have the possibility of doing an exact sampling. OK, and of course, we don't get a free lunch here. So even if I have a biased model, you might say, well, OK, then I can just write down any model, and I'll get the correct answer. And of course, that's true. But the worse your model is, the higher the variance of these reweighting factors. So if Q is not really close to this e to the minus action probability density at all, then these reweighting factors will fluctuate very strongly, and they will add a lot of noise and a lot of variance to any measurements that I make. And so if we want to understand our model quality, one useful metric is the variance of those reweighting factors. And an equivalent metric, in some sense, is this so-called effective sample size, which is just related somehow to moments of these, the distributions of these reweighting factors. But the intuitive meaning of this is just simply, if I draw n samples from my model distribution, what fraction of those, the ESS tells me what fraction of those are useful effective samples from my target distribution. So you want this to be close to 1. ESS of 1 would correspond to 0 variance of your reweighting factors, would correspond to a perfect model. An ESS of 0 or an infinite variance of the reweighting factors corresponds, of course, to a useless model that tells me no information. And realistically, we probably end up somewhere in between the two. But as long as you have some measure of this quality, you can try to optimize along this line. I'll come back to the optimization that one uses to these parameterizations. Yeah?
It looks a lot like the factor you would estimate for the overlap problem.
Yep.
And there you can always argue that it scales badly with the volume because you have a ratio of 2x.
Yeah, you're asking exactly the right and the hard questions. So what one can say is, if my model distribution Q is also written as some kind of local action, so if the way the model is constructed is such that the density turns out to be local, then this ratio is extensive in the number of degrees of freedom. So this is going to scale exponentially poorly in the number of physical correlation lengths that are packed into my box. That is certainly true, and is one of the challenges, I think, of this approach. The other thing, though, to mention is that we're not often after necessarily the infinite volume limit in a practical calculation. We're after calculations at some set of volumes that are sufficiently large to capture, well, in QCD, enough pion correlation lengths, let's say, in the box. And so if you can capture that, if you can capture that sufficiently well, maybe it doesn't scale to like 100 Fermi to the fourth box, but you might still be happy with what you've got. I think that's essentially the answer we've got at the moment, and it is a challenge to be kept in mind, absolutely. Okay. So I should maybe highlight that this actually can work. This is just a marketing plot, apologies, but basically, in at least one case, we've seen that, for example, when we apply these flow-based samplers compared to traditional sampling methods like hybrid Monte Carlo or heat bath, then if I look at the measure of cost versus scaling this gauge coupling beta towards the continuum limit, you get a much flatter scaling of cost with the flow-based method versus with these traditional methods. And in this case, this was a 2D U1 gauge theory. So this had to do with a topology of the theory that is very rapidly mixed over Markov chain steps, or in other words, over samples drawn from the flow, versus topological freezing that sets in when I use traditional samplers so that they very rarely hop between these different winding number sectors of the theory. And that fundamentally just comes down to the fact that the way we're drawing samples in this approach is not a Markov chain, but via independent samples, like independent random noise that's being passed through the model in parallel. So you can get a good effective representation of the distribution. All right. Any other questions? OK, so now to the more experimental part. Because I could talk at you all day about these finer details of these flows, but I think, at least personally, I'm quite the opposite of Gert. I don't understand anything analytically. I understand things only when I write them in code. So for me, at least, this is how I would have wanted this presented, and I hope this is useful to some of you. So I think, because I'll change screen here, let me write this down here. I've got a bit of code, and I would encourage you to follow along if you are interested on your laptop. But it is not necessary. This will be working with Python, and I provided some setup instructions that are hopefully not too complicated, which is always a bit of a challenge when setting up environments, but we'll see if this works out. So yeah, I should say the summary of what hopefully we'll just work through is really to just get two things done. One is maybe a bit of a bigger task. But I think it's useful to understand critical slowing down by actually writing the hybrid Monte Carlo sampler for a phi to the 4 scalar field theory. And we won't go into much detail on this because I'm sure Jakob will talk more about critical slowing down and sampling. But this provides a basis for exploration, maybe even also complementary to his lectures. And then I think perhaps more interesting and more relevant, we'll implement a toy flow-based sampler that doesn't involve any machine learning yet. It's just to see how this sampling procedure works, how we estimate densities, and so on. OK, so I'm giving you a little bit of time to go check out this GitHub page. There's a README on there which has some of the setup instructions. But the relevant thing is that if you do have this, you should eventually be able to open up a Jupyter notebook. This is a little bit hard to read, isn't it, from the back, right? OK, let me see if I can zoom in on that. How's that? Can you read the small text in the back? Still too small? So? Here, let me just make it a little bit bigger. OK. Hopefully that is a little bit better. OK, so there's a couple things. Probably the first thing to ask is, how many people have worked with Python to some extent before? Oh, yes. OK. I was a little bit worried. It's OK if you haven't. I think the nice thing about working with Python here is that it's generally very close to natural language. So it should be a bit readable what's going on, even if you've just worked with C or something else. OK. And most of what we're going to be working with here is playing a little bit with PyTorch, which is a framework for machine learning. And in many ways, the types of things you do in PyTorch are very similar to NumPy, if that's something you've worked with. But the idea being that you operate on arrays directly, or in the PyTorch lingo, tensors. And you operate on them as a batch, essentially. So for example, if I have a field configuration phi, the way I would represent it is by a torch tensor. And then if I want phi squared per site, I just write phi squared. And I better actually start writing some things instead of saying some things. So let me, first of all, just grab a bit of these packages that we'll be working with. And I should mention, this is the other thing I should mention. There's, as with any good cooking show, a pre-baked version of this notebook. So if we do get stuck, or if you just want to read along, it's just called Lecture 1. But the Lecture 1 skeleton has the version that hopefully we can fill in together. And I do think it's useful for learning to type things out. So I'd encourage you to follow along in that regard if you'd like. OK, so there's basically three things that we're going to work with. There's some plotting. There's NumPy itself. And there's PyTorch. And so PyTorch is going to be mainly the thing we work with for the reason that as we move towards machine learning, we will use some of the machine learning tools. But actually, it also makes life a lot more convenient when we try to write certain lattice field theory algorithms. What I will do is I will also make these plots a little bit nicer. And hopefully, that's a reasonable starting point. So to get a little bit of a handle on PyTorch, I think one thing to do is just to say, OK, well, what is like a relevant object, PyTorch object? What does a relevant tensor look like? So let me draw a Gaussian distributed. So this is random normal is what this stands for, field. And I'm going to give it an 8x8 shape. So this will look like an 8x8 lattice, for example. And in order to see what that actually looks like to begin with, well, let's actually plot it. So OK, I've drawn some random normal field, very uninteresting, but it is an 8x8 field. And in fact, matplotlib, this library which I'm using to plot, understands torch tensors, or understands how to convert torch tensors into something usable. So I've just plugged it into this imshow command to show graphically what that field configuration looks like. And if you prefer the non-graphical version, just to understand what's actually inside this thing, it's a torch tensor, and it has a bunch of real numbers inside it. And as you can perhaps eyeball, they are indeed distributed Gaussian-like. OK, so this is a bit of a starting point. And then one thing I did want to point out is that in order to compute things that appear inside our action, which for phi-4 theory on the lattice discretization is going to involve terms like nearest neighbor products of scalar field components like phi x plus mu hat. The way we might do this over entire tensors is to use this roll utility. And so what that precisely does is perhaps also easiest to show if I just do something like this, by showing side by side what the rolled and unrolled version of a field looks like. So what this does is it's just going to rotate my field according to periodic boundary conditions by one lattice spacing in, let's say, the 0th dimension. So that's, if I can do this correctly, dims, yeah. That's just shifted my entire lattice field down by one lattice unit, if you can kind of eyeball where the equivalent points have gone. So for example, I can now do element-wise products between these to get my phi x times phi x plus mu hat everywhere on the lattice. We'll come back to that in a moment. I can, of course, also roll in the other dimension. This is perhaps uninteresting, but of course, that shifts side by side instead of up and down. Okay, so this is just a little bit of getting familiar with PyTorch. Now comes the interesting bits. So what I've done is I've just pulled the action. Yeah. Yeah, absolutely.
This loading thing, does it produce a view to the memory location, or does it allocate a new
I believe it produces a view. It certainly should, to be efficient, produce a view, meaning that it doesn't copy the entire memory, but it just says, here's a little bit of the data structure on top of the old memory. Roll is a bit of a weird one because it actually does shuffle your memory around, and so it's not, I'm not 100% certain that PyTorch actually does, but it should, I think, if it's doing things sensibly. Yeah, so this is maybe worth mentioning in general. So often, I'll do some kind of operation where it doesn't make sense to entirely copy the entire lattice configuration and do the operation, but it makes sense to just implicitly hold in memory the fact that I did the operation on that other lattice. And this is the view that Alberto is talking about. So that's one of the ways that PyTorch makes, and actually NumPy as well, makes certain things much more efficient to do, even though we're working with Python at the end of the day. OK, so let's get into a little bit of physics now that we've just very, very barely gotten familiar with some of the notions of PyTorch. So what I'd like to do is play a little bit with the action for the phi-4 theory, but I need a lattice discretization of that. And so I'm going to use this continuum parameterization, which involves m²/2 lambda over 4 factorial, the usual phi-4 potential, and this discretization of the d mu phi squared term. So if you like, my continuum action should have something like a 1/2 d mu phi squared. And what's happened here is I've just done an integration by parts to get that this is equal to phi d squared phi. And this Laplacian being applied to phi in discretized form is just this guy in parentheses here. So if we compute that, that's our kinetic term. And the other components are just our potential. And we can rearrange this a little bit because you might notice that I've got a phi x squared, which looks a lot like my phi x squared here. So if I just pull that part of the summation out, that's my extra factor of nd. And so this is very simply written in terms of two local terms and a nearest neighbor type of product. OK, so let's actually try to implement this. And what I'll do is I'll just say, well, first of all, I want to be able to specify what these m² and lambda parameters are. So I'm just going to take those as arguments and hang on to them. And then if I'm given a field configuration, I want to be able to evaluate what is this action. So maybe let me scroll this slightly. I want to be able to just, given some field configuration phi, which is a two-dimensional torch tensor, I want to evaluate this summation over prefactor times phi squared and prefactor times phi to the 4 and the nearest neighbor term. So, well, the prefactors I know. So we have this m² term over 2 times phi squared. And the lambda phi to the 4 term is going to look like, well, just lambda over our 4 factorial. Let's drop that here, phi to the 4. And I'm just going to sum over all the sites. So this is the local part of the potential in the action. The more challenging part is this nearest neighbor interaction, but we can easily set this up with the roll. By iterating over the 2 dimensions of my space-time grid, I'm just hard-coding everything to 2D here because this is a demo. And all we need to do is take this torch roll of phi. In this case, what I'm going to do is roll it by -1. So I'm saying take my lattice field configuration, take a shifted version that goes backwards by 1. And that's going to give me my product of phi at x and phi at x plus mu hat if I multiply these together. And there's a minus sign here. And this needs to be summed over all the lattice sites. So maybe the syntax is unfamiliar. Don't worry about it. What's important is the general idea of what's going on here, which is this is just providing me some way of plugging in a field configuration and getting the action, which is a very fundamental operation that I'd like to do. And now if I've done things correctly, I should be able to, for example, take this phi that I had before. let me just make an action with, I don't know, some particular parameters. And I should be able to apply or measure the action of that field configuration. And it would help if I printed what that was. There's no return. Thank you. Indeed. OK. So we have some number. It's fairly meaningless in the abstract sense. But we have the ability now to at least evaluate that action, which is a good start. So the next thing that we'll need, and the final thing that we need inside this evaluation of the action, is the grading of the action, because this is what shows up inside many of our sampling algorithms. So we need to be able to take the derivative with respect to a scalar field phi of x of this action. And OK, we could go to this functional form. We could try to do that derivative out and figure out what it should be. But this is where PyTorch's utilities for doing gradients automatically is a massive boon, because I can just say the gradient of this is going to be torch func grad of value. And if I've done that correctly, we should be able to just get also the gradient of the action, which, because it's a gradient, it is an 8x8 tensor, or in general, it has the structure of the field configuration, which tells me how each component of the field wants to be transformed to minimize, or rather in this case, maximize the action. OK, so if you've ever implemented HMC by hand, hopefully this is seeming a little bit magic and convenient, because writing out gradients by hand and testing them is a huge pain. I wouldn't encourage you to actually implement HMC this way. It's maybe not the most efficient approach, but it gives a nice way of just quickly prototyping things. So for that reason, I think it's quite interesting. OK, so we, in principle, have captured everything about our theory in this action functional, but we don't yet have a way of actually sampling according to a given action. And yeah?
Do you think it does a finite difference for the gradient, or does it actually?
No, so the way this grad is implemented, it's actually documented. It forms a computational graph. So it evaluates all of the steps that go into computing S in a forward pass. And then it uses this backpropagation algorithm from machine learning, which says, if I have some perturbation to the action, how does that affect the prior step to computing the action? Actually, I could probably even show it here. So what backpropagation is essentially trying to do is say, if I have made some perturbation to my action here, how does that correspond to, or how is that sensitive to perturbations of the components that went into this calculation, propagating that sensitivity, which is some kind of like tangent vector, backwards through the operations that were done to compute S. So there's a downside of this, which is that you have to build up that entire computational graph and then go backwards through it. Certainly not the most efficient way, but it's automatic and certainly guaranteed to be exact. No numerical approximations there. This is something I'd be happy to talk about more, but since it's a little incidental to the actual subject of the lectures, I think maybe we should stay on track given the limited time. But it is, yeah, so I mean, this is one of the things that PyTorch is very good for, is that these kind of particular algorithms for evaluating gradients and derivatives are just are easy to work with. And this backpropagation is sort of the bread and butter of how do you get gradients out of scalar functions. So it works equally well for the gradient of an action as it does for the gradient of a scalar loss function in a machine learning case. OK, very good. Hopefully everybody's had a chance to follow along here. OK, so the next bit here would be to actually draw samples according to this action. And I am perhaps previewing a bit Jakob's talk. Were you planning to go into the details of HMC? OK, very good. So then I don't need to say too much. But what I will say is, effectively, if I want a sample from this distribution, e to the minus action normalized by my partition function, this is the same thing as integrating over a field that I'll call pi. So this is exactly the same shape and dimensionality as phi. And typically it would be called the conjugate momentum field for reasons that will become clear in a second. I'll give it a Gaussian distribution, and I'll leave everything else the same. OK, and I have to put some kind of normalization that normalizes out the Gaussian. But otherwise, I've just added in an integral that should integrate to 1. And so nothing has changed. And the idea behind HMC is simply that if I draw samples now of this pi, and I perform, and I think of rather this as being an e to the minus some kind of Hamiltonian function h, which if you remember your Hamiltonian dynamics, this should look something like a momentum squared and a potential term. I can in principle do an energy conserving evolution of this pi and phi field, which are going to mix them together and preserve exactly this e to the minus h. And the reason that this works, I'll leave off to Jakob's lecture. This is really treading too far in that direction. But essentially, I think I just want to summarize that I can perform sampling by drawing this field pi from a normal distribution, and then evolving according to the Hamilton equations of motion, which say my phi dot is pi, and my pi dot is minus grad s phi. And if I do these two things, I should be able to then have a distribution that asymptotes after many iterations of this towards my distribution of interest. So this is the fundamental idea behind HMC. The reason that I think we should play around with it a little bit here is because it gives us an insight into the critical slowing down problem, which we can get access to already in this phi-4 theory. Now, the key component of this was these equations of motion. So that is some kind of evolution according to a fictitious Monte Carlo time of my field configuration according to pi, and of these momenta according to the gradient of s. But we have all the ingredients to do this. I know how to compute the gradient of s. We've just looked at that above. And to do evolution in time, I'm just going to do a simple discretization. So the simplest thing I could do, perhaps I'd better even write it out here because it's easy enough to state in code. The simplest thing I can do if I want to update, given a phi and this momentum pi, according to these equations of motion, would be to iterate for some number of steps, which I'll call, for reasons that will become clear in a moment, leapfrog steps with certain step size. Let me just iterate over those steps and say, well, my phi on a given step, I should add dt times my pi. Easy enough. And my pi on the given step, I should subtract dt times the gradient of the action evaluated at phi. So because we've built up all these components, and because PyTorch takes care for us of doing this across the whole array at once, writing down this evolution equation is just a straightforward, basically 2 steps. And there's one minor tweak that's useful to do here to make this sampling work effectively, and that's to symmetrize this process. So right now, I've evolved first my field configuration phi, then I involve my momenta, then field configuration, then momenta. So if you like, I've done something like phi goes to phi 1, then pi goes to pi 0 goes to pi 1, phi 1 goes to phi 2, and so on. So because I started with a phi, and eventually I'm going to end with an update to pi, this is asymmetric and actually has slightly worse convergent properties than if I symmetrize this by simply chopping off half of the update step. So I go first by a factor of d over 2. And at the end, I do half an update step to my phi, again by a factor of d over 2. This is known as a leapfrog update because if I picture in time what's happening to my pi and my phi goes halfway, pi conditioned on that leapfrogs across it, phi conditioned on that leapfrogs across it, etc. And at the end, you have half a step here. So you have this kind of hopping over the previous evaluation with this nice symmetry property. And there's various reasons why you might want that, but it slightly improves, in our case, and for our purposes, the convergence of this HMC sampler. So long story short, let's chop off that half step. Let's put it at the end. And to do that, what I'll do is I'll explicitly reduce this number of steps by 1. I'll put, and it's probably actually easiest if I do the following. I'll write this down here. Put half a step here. So that's a dt over 2. And since I'm missing one of the full steps, that's got to go outside the loop, and the final half a step. So I've taken basically a very simple integrator, and I've just slightly perturbed it so it has a symmetry property. But it's exactly integrating these Hamiltonian equations of motion, which has to do, again, with sampling and evolving according to this conservative update using the Hamiltonian equations of motion. OK, so why all this fuss? I'm going to skip looking carefully at the analysis of how that integrator performs versus another integrator. This is something that you could explore if you're interested in. What we can do with this is now actually draw samples. So recall that I'm missing one step, which is drawing these momenta from the normal distribution and doing some kind of evolution, which we now have implemented. So let's add this step to the list. And if we loop over this multiple times, those are iterations of our Markov chain evolution according to HMC. So what do I need to do? Well, I need some starting configuration for my Markov chain. If you recall this picture with the topological charges, I said you can start with anything arbitrary. In principle, this should stochastically mix and converge to the right equilibrium distribution. So what is a good arbitrary starting point? Any ideas? Suggestions? Identity, yeah, sure. Yeah, sorry. So what does identity mean for a scalar field? Sure, we can just set phi of x equals 1. There's a shortcut for this in PyTorch, because of course there is. So I'll just write torch.ones. That's a reasonable starting field. And I've set up this call to have some number of thermalization steps, because we're starting from some fixed configuration, which is clearly not sampled from the right distribution, and some number of full iterations. And often we don't want to measure everything, every step of the Markov chain evolution, because that would be an enormous number of measurements. So we'll get to this parameter in a moment. But the idea being that we don't have to sample, we don't have to measure every single iteration of the Markov chain. And this specifies how frequently we should do that. And these are just parameters for this HMC evolution that I talked about before. So what do we want to do with this? Well, we want to do some number of these thermalization updates. And we'll figure out what those updates look like in a second. Then we want to do our general updates, where we're going to actually save some samples, some measurements of our samples. And both of these updates are going to look the same, except this will involve some sort of measurement inside, where we store some information about the configuration. Question?
What is the star after the action?
Yeah, sorry, I'm using a little archaic Python syntax. What this means is that you're forced to pass all of these arguments by keyword, by explicit keyword argument. So I have to write, as you see down here, I have to write, when I call this, n therm equals 100, n iter equals 100, and so on. It's just force of habit. It's a nice way to ensure that you see what's actually being parameterized instead of just random numbers going in. Yeah. OK, so we should write down what one of these updates actually looks like. But we've got that up here on the board. So I should draw my pi from some normal distribution with the same shape and structure as phi. And we've seen how to draw random normal fields up above when we tested this. So let's just copy that. Oops. So I'm just going to draw my pi field. Then we want to apply this update, which took my phi, my pi, and what else? The action that I'm trying to update according to, my dt, and my number of steps. So that's doing some kind of update to the pi and phi field that updates according to these Hamiltonian dynamics, as we just talked about. And Now we could be careful here, and one should be careful about worrying about integration error, and you should apply a metropolis accept reject step, but I'm not going to worry about that because this is not the Monte Carlo lecture, even though it seems like it. What we're going to do is we're just going to take the phi that comes out and say that's our sample. So we're done. We do that also for the normal updates, except now what I want to do is just if my I is 0 mod the number, the frequency of the measurement, so just every nmes steps, I want to save out some information about my field. And there's a number of things you could measure. You can measure correlation functions, whatever. But what I'm going to measure, I'm just going to make an array for this. What I'm going to measure is just the average value of phi. So this is, I can call it phi bar, for example, as it's often called. This is just the volume average of the field phi. And the reason we might be interested in this is if we're in a broken symmetry phase of this phi4 potential, then we'll see that this average phi should take on a non-zero vacuum expectation value. And if our Markov chain is good, we should see tunneling between the two different minima. And in the symmetric phase, we should see that it has just a single, it takes on an average the value 0, and not a double peaked structure in a histogram of this observable. So that's all we want to take a look at, and why don't we just return that out of this function? Just to make things slightly more convenient, let's just put this in a dictionary. This is also, again, just slightly force of habit, but I've assumed it slightly further down. Just in case we wanted to add extra things to return from this function later, then we could add extra pieces to this return. But OK, so that's HMC in a nutshell. I didn't expect to actually cover the entirety of it, but here we are. Now, back to physics for a second. So we're taking a look at this phi4 theory. There's two bare coupling parameters. There's the bare mass squared, and then there's the bare quartic coupling. And so this is a phase diagram on a much larger lattice, but it should still tell us, roughly characteristically speaking, how our phase diagram looks even on our 8x8 volume. And what it tells us is that we're in a broken symmetry phase where the vacuum expectation value of phi is not 0, when for a given value of the bare mass, our lambda is sufficiently small. And otherwise, we're in the symmetric phase. And so what I thought would be reasonable is if we just pick some particular value of this bare mass squared. So here, minus 0.5, that's this vertical line. And we can choose two values of lambda, one which is slightly above the phase transition, one which is slightly below. And we should see the difference in the phase structure. And the two values that seemed reasonable to pick here were around 1.5 and 4.5. But in principle, you should be able to play around with this on your own and try to understand exactly where that transition appears to line up in this finite volume. And if you're feeling ambitious, you could also attempt to scale the volume and look very carefully at how this phase diagram was produced. That's not related to this lecture, but just out of interest. OK, so we can actually now go ahead and run this. We'll take our broken phase action. I've just picked out some random parameters. So we're skipping 100 steps. We're doing 100 steps, and we'll measure each of those. Sorry, we're doing 1,000 steps of proper Markov chain Monte Carlo, and we'll measure for each of those steps. So let's just give that a shot. And likewise for the symmetric phase action. And let's hope that I haven't screwed something up, because it should otherwise just go through pretty quickly. Perfect. OK, so we've got some stuff out. But it would be useful if we can actually see what happened here. So let's make a quick plot of that. And what I think will be useful is if we plot the history of these observations. Now here's the moment of truth. Did we actually do something reasonable? Very good. So if you notice, this is the broken symmetry phase. And the average phi is fluctuating around a non-zero value. So that's good. It's not fluctuating about 0. And for the symmetric phase, it is fluctuating about 0. So that's excellent to see. Now, of course, what would be nice to see is if we ran this long enough, this blue trajectory here should eventually tunnel over to the negative vacuum as well. But we have limited time. I leave it up to you to explore that if you'd like. And if you do that, actually, the parameters I chose in the filled out version of the notebook do successfully tunnel, probably just a different random seed. And then you could build, for example, a histogram, looking at what is the distribution of this phi bar quantity. And what you'll see in the broken phase is a double peak structure. And in the symmetric phase, of course, a single peak structure. OK, so why did I spend all this time going into this? Well, it's because, as we can obviously see, the Monte Carlo in the broken phase is significantly frozen into one vacuum and is not accurately sampling the distribution. Because the distribution is symmetric around phi goes to minus phi, we should expect to see equal numbers of configurations that are in one of the vacua as in this negative vacuum, which is not sampled here. And hopefully, if things go well, by lecture 3, we will try to solve this using a flow-based sampler. But because we're not quite there yet, with the last, I have 20 minutes left, right? Roughly? A little bit less? Yeah. OK, perfect. So that gives enough time to take a hard right turn and actually do the thing that I said I was going to do, which is look at normalizing flows. And instead of looking at a full flow transformation for a field theory, we can look at a flow similar to that cartoon plot I showed, just over 2 variables to understand what are the relevant considerations, how does the sampling work, how do I get out the density from the model, and how, for example, would I then compare this against the target distribution that I'm interested in. And the idea is that these 2 branching endeavors will eventually merge. So we have now played with our phi-4 theory. Here we'll play with a toy theory with flows. And eventually, we'd like to do flows for the phi-4 theory, which we'll come back to. OK, so as you can read up here, I've just come up with some very arbitrary synthetic flow transformation that we could apply. So the prior distribution is a very straightforward one. It's just on my 2 variables. They're both a unit variance Gaussian. And the flow to be integrated, which tells me the time derivative of this 2-component vector, is something that's a little bit arbitrary, but I've designed it for the reason of creating a double peak distribution, which is somewhat interesting. And the way you can see that is, well, OK, in the 1 component, this flow is just taking my samples and it's reducing the magnitude of x1 because it's always flowing oppositely to the current value of x1. But the interesting thing happens in the 0 component, where I have this what is going to turn out to be an S-shaped structure. And actually, I think it's useful if I just plot what that looks like for a second here. Between, I don't know, 5 and 5. And then the 0th component of this velocity field is that x times the exponential of minus x0 squared over 2. So let's just give that a look. So this is the velocity field as a function of this x0. And so you can see when x0 is in this region from, let's say, 0 to 2, the velocity field is positive, so it pushes x0 even more positive. When it's in this region from 0 to minus 2, it's negative, so it pushes our x0 even more negative. And so what that's going to do is, if we have initially a Gaussian, the positive samples are going to go more positive, negative samples more negative, and we'll form some kind of double peak structure by pushing these samples around. That's the analytic idea, but let's actually see that play out now. So OK, I'm going to make this a little bit smaller just to get this out of the way. So what we need to actually do that is, well, first of all, we need to implement what is that b, which tells us what is the time derivative of my samples. And then we're going to need to implement a function that actually takes the samples and integrates this ordinary differential equation forward in time. So keeping in mind that what I want at the end of the day is to integrate that x dot equals b of x. These are each 2-component vectors. And I want to integrate it arbitrarily. I'm choosing that my flow will go up to t equals 1. And that's the distribution that my model is going to be outputting. But you can see I've also specified in this function some arbitrary TF. And the utility of that is that if I integrate it not all the way up to 1, we can look at intermediate distributions to understand exactly how the samples are moving along until we reach that target distribution that we're after. OK, so let's, again, jump back into a little bit of code here. So one thing I'd like to do with this velocity is, given this 2-component vector x, I'd like to be able to evaluate the 2-component velocity field. And to put 2 components together, I'm just going to stack an array of length 2. The first component of which was this x0 e to the minus x naught squared. Actually, I've already written it out mostly, so we can just grab that. And it'll be useful to split apart the components of x. And this is not numpy. This should be torch. And if you remember the velocity field, the second component was just minus x1. So exactly just implementing this 2-component vector velocity as a function of my 2-component x. And I suppose I should actually return that. Otherwise, that would be not very useful. Now, there is one other thing that we need from this velocity field, which is the divergence. And the reason this comes into play is that, well, you may recall that I wrote before in the slides that this is actually, you could choose to write it as the gradient of some scalar function, or equivalently, we can just write it as a 2-component vector. But what I need to get my, I should write it maybe a little higher. What I need to get my log Jacobian, log determinant of the Jacobian, is to be able to integrate from 0 to 1 up to some signs that we'll come back to, the Laplacian of phi. But that's just equal to the divergence of this B field. So what I'm after, to understand how my density has squished and stretched, is to integrate the divergence of B. And hopefully intuitively this makes sense. Where the divergence of the velocity field is positive, my samples are moving apart from each other. Therefore, the Jacobian is going to be, the determinant of the Jacobian is going to be negative. And where the divergence is positive, the samples are moving together, and the determinant of the Jacobian, the Jacobian is telling me how the volume form is changing, so that will be negative. But essentially, this is telling me about the squishing and stretching of the density as a function of time. And therefore, I need to integrate it to understand what is my final density at t equals 1. OK. So maybe I should briefly pause. Any questions so far on getting our teeth into flows? No? All right. OK. So we could use some auto-differentiation tricks to figure out what is the divergence of B. That's sometimes convenient. In this case, I just want to quickly get to the answer. And so I've written it out, just simply differentiating the 2 components. And so we want to implement this function of 1 minus x squared, x0 squared times this exponential minus 1. OK. So let's just get that dropped in here. Again, we can just separate the 2 components of x. And we had 1 minus x0 squared times this exponential minus 1. OK, so that's the divergence of our velocity field. OK, now, and finally, the sort of interesting bit of actually evolving according to this velocity field. So if I have some initial sample x, and velocity here is going to be an instance of this class, I want to use calls to velocity.value and velocity.div to update my x and also to compute the Jacobian. So updating the x, it's not hard. Yeah, I've also, of course, dropped in some parameters that lets me tune how many steps I'm going to use to integrate this. So what I'll do is iterate over those n steps. And I'm going to take my x and just update it according to the measurement of the velocity at that current value of x. So this is a simple first-order discretization of our differential equation up here. that's all well and good. But we also want this Jacobian, and now I'd better think carefully about my signs and make sure I've got this correct. So my divergence, if that's positive, is expanding my volume element, and therefore the log that j should also be positive. So that's good. These signs should hopefully be working out. And what I'm going to do, I'm going to start this at a value of 0 and accumulate according to this differential equation where I've conveniently forgot what the infinitesimal element is. We're going to accumulate dt times the divergence of this velocity field. And just spit both of those out. OK, so what am I forgetting? Yes?
Yeah, I think you haven't defined dt.
Thank you. Exactly. So what we're forgetting is that dt should here be what in terms of my variables?
TF divided by n.
Yeah, tf over n step. Perfect. And that means that after n steps, I will have reached tf equals whatever the argument was, whether that's 1, 1/2. I could actually flow beyond 1 if I wanted. But the model distribution, just canonically that I'm deciding that I'll be after, will be tf equals 1. OK, so I've also left this keyword argument to allow me to flow in the reverse direction. And for the sake of what we'll want to do to evaluate the model density here, let me actually get that implemented as well. So what needs to change here to flow in the inverse direction? There's a couple things. Yeah.
dt.
Sorry?
You change the sign of dt.
Change the sign of dt, yep. So let's just do that. Sorry? And the Jacobian, in which way? Yeah, so if we flip dt, what we will get without changing anything else is the Jacobian for the inverse transformation. I think it's convenient to just keep the Jacobian as consistently the forward transformation, so it's exactly what you said, that we should also, in that case, flip what the sign is here. But I don't know, yeah. Sorry? So this, you mean the direction that x is being updated in. This is, I think, going to be encoded in this fact. So we've kind of packaged this all together and said dt is going to be negative if we're doing the inverse. So that means that x is updated in the opposite direction. And what I'm going to do for simplicity is I'm going to leave this Jacobian as it is, which means that when I integrate in the reverse direction, it gives me the Jacobian of the reverse transformation. And we'll just have to account for that. But there is one more thing that we might need to do if we had a sort of time dependence baked into our measurement of the velocity field. In this case, we don't, because our B is a time-independent velocity field. If we did, we might need to pass, for example, some sort of arguments like this here. And the t here that we compute would have to be different depending on which way we're evaluating. Since we're not doing that, we're not going to worry about that for the moment. And I think this flip of the sign is actually all we need to just integrate in the reverse direction. Unless I'm forgetting something, which we'll find out momentarily. OK, so we've almost got there. We can now take our velocity field. We can integrate the flow. And actually, probably what's useful is just to see that that works. So let me write down an x. Put it at, I don't know, 1.0, 0.0. And then, well, I guess we had better make a velocity. And let's integrate this forward for 100 steps to tf equals 1. It would help if I actually print something. So OK, so we've evolved from 1, 0 to whatever this number is, 1.55 something, 0. That's in line with what we thought this flow should be doing, pushing positive samples more positive. If I flip the sign here, presumably, yeah, pushes my negative samples more negative. So this is exactly this picture of forming this double peak structure according to this velocity field that we have. Now, another thing we could do very quickly is we could say, let me just try to reproduce what that original sample was by flowing backwards through this flow. And if that's the case, then my x2 should come back approximately to the right structure. I've clearly done something wrong. And what have I lost here?
XP has the log j.
XP has log j, thank you. So we get some log j out here. We get some log j2. And one thing I should be a little careful of is, because I'm mutating the variable, I just want to make a copy of it before feeding it into flow. OK, so up to integration error, we started from -1, 0. We flowed up to -1.55, whatever. And then we flowed back to approximately -1, 0. So this is reasonable given 100 steps discretization, and we could improve this by changing our steps. OK, so this all seems to be working. Now, one thing that's probably useful to do.
Other problems of finite arithmetic precision in this game of going back and forth?
Sure, yeah. I mean, if we were doing some particularly gnarly calculation inside the velocity field, or if our flow or our velocity field was particularly generating chaotic flows, then you can certainly imagine that the precision of your floating point numbers matters.
For example, the typical case, even in the scalar field theory, it can be that in one direction you have a Laplacian and in the other the inverse. So the most typical case is that one thing is the heat equation in the wrong direction.
Yeah, absolutely. And so, OK, there's ways to address that. But if you don't mind, I'll just table that question for now and say, yes, generically, there are issues with precision, and then one should think harder about it. In practice, it can be. So for example, often when we run these kind of flows with float 32, you get crazy answers. And then with float 64, things are pretty stable, even for field theories. But you don't know that you're not missing. Well, actually, you do know, rather, if you are missing issues, because you can always run backwards. And you can check that you stably reproduce your initial sample. Yep. OK, but yeah, this is a good point. And I hope to return to that if there's time. OK. So we're pretty close to the end of just playing around with this flow. I mean, we haven't really done anything with it yet. So I want to use the last 5 minutes to actually sample using this flow. And what I said, if you recall back at the summary here, is that this flow is, well, it's this evolution according to this velocity field. But it's also starting from this prior distribution. And together that defines my flow model. So it says start from samples from this normal distribution, then apply this flow. And whatever the output samples are, that's my flow model distribution. And so actually doing that, it's a very small modification of what we have here. Instead of just taking one sample, let's again draw some random normal variables. And I'll draw, I don't know, 1,000 of them. They each have 2 components. So that's what this tuple argument means. This is all going to look the same. There's one minor change that needs to be made, because this flow expects a single 2-component vector, and everything we wrote assumes that. We're going to have to use one of Torch's amazing features to make a batched version of this flow, which can be done pretty simply by just wrapping the flow in this vmap call. And there's only one thing we have to be careful of, is saying, well, it's just the first argument that has the batch dimension we want to parallelize over this number of samples. And so if we do that, we just make this flow batch, flow batch. Let's actually forget about flowing backwards for now. Just make sure that works, which it doesn't. And let's just double check. What have I done here? Yeah, I probably should be a little more careful about how I do this. So let's just try that.
I think you're inputting X and not XR.
Oh, well, thank you. So I don't need to be more careful at all. OK, what have I lost? Lost something along the way. Yeah, so the other thing that would be perhaps helpful is if I don't do this in place. Just double check if that causes the problem. OK, well, PyTorch weirdness. OK, so let's just take a look at what we've got. So I'm going to plot the 2 distributions side by side. And what do we want to do here? Let's make a 2D histogram, perhaps, of And there's one thing that I would like to do before I pass this into the histogram, which is just what do I want to do? Turn this into a NumPy array. So this should histogram my initial distribution. Just double check that that works. Looks like a normal distribution to me. And this should histogram our flow output. Again, OK, I want to turn this into a NumPy array. XP, XP. OK, this resolution kind of is terrible, so let's increase that. And it's probably nice if this is a flat aspect ratio from -3 to 3. OK, so not the most interesting example in the world. And one thing that'll maybe make this slightly better is if I add a little bit more samples. Yeah, now you can really see what's going on. So after flowing for some amount of time, I've taken my normal distribution, and it's squished down one of the axes, and it's stretched and pulled apart into two different peaks here, the samples. Now, there's more that we could play around with here, but I think because we're at time, it's best if I leave some of this for the exercises, which anyway, building on this was part of the exercises. And so what I will leave as kind of an open question is, can you use this Jacobian to actually measure log q as a function of this x and reproduce this histogram with an analytical evaluation of log q? And if we've implemented our flow correctly, we should find that we could just arbitrarily plug in a point, we can measure our log q, and it should give us this probability density that we see empirically here back. And as long as those two things match, we have the two things that I said are important for our flow-based sampler, one being that we can draw samples efficiently, and the other being that we can measure the density, which allows us to apply a bias correction factor. So OK, with that, I think I should conclude the first lecture. Thanks very much for your patience with this.